Hello, continuing with our proof by inductions with divisibility, we're going to be looking at this type of situation here. So this is going to be very similar to the style that we did before, but it looks a little bit different, so I wanted to touch on it. So I'm going to follow my same steps in proof by induction as I have so far. I'm going to start at part 1 with n is equal to 1, and I'm going to sub in n is equal to 1 and see if that is divisible by 4. So I have 5 to the power of 1 minus 4 by 1 plus 3 is equal to 5 minus 4 is 1 plus 3 is 4. 4 divided by 4 is 1. Therefore, it is divisible at n is equal to 1. Now I know for part 2, I'm going to state that I assume that my relationship holds for n is equal to k, and I want to write down what I mean by that. I'm going to say that n to the power of k minus 4k plus 3 is going to be divisible by 4. If I divide it by 4, I'm going to get some, sorry, I'll call that m and not n, some m where m is an integer. That's what it means to be divisible by 4. So I'm going to assume that that is divisible by 4. Part 3, where our maths really starts to begin. With divisibility proofs, I'm going to write down what n is equal to k looks like, and I'm going to use the fact that I'm assuming n is equal to k is true. So assume that it's true. I'm going to use the fact that I'm assuming n is equal to k is true in combination with rearranging the n is equal to k plus 1 position to show that n equals to k plus 1 must also be divisible by 4. So if n is equal to k is true, then n is equal to k plus 1 is true. That's what we're going to show, and with divisibility we start out with the n is equal to k plus 1 position. So I have this situation here, and I have the powers added, which means the base numbers must have been multiplied together. So I have 5 to the power of 1 multiplied by 5 to the power of k minus 4k minus 4 plus 3. Be careful at this point. We are very used to, since first year, adding like terms together. This is an instance where you don't want to do that, because what we're going to use is that minus 4 is divisible by 4, and I'm going to use, well, I will look at it in just a second, but we're going to use this plus 3 to form part of our n is equal to k situation. So in this type of proof, you need to be careful not always to add up like terms. A reminder that this step here gets you to 50% of the marks. So before you've done this, you should have 50% of the marks, or approximately 50% of the marks, at this line where we've done no rearranging. Now, I know that I want this to end up being divisible by 4, so I'm going to break this up as cleverly as I can into stuff that is going to maybe link back to n equals k, and try and give me something that's divisible by 4, which is fairly straightforwardly going to be 1 plus 4 by 5 to the power of k minus 4k minus 4 plus 3. So I get 5 to the power of k, 1 plus 4 on 5 to the power of k minus 4k minus 4 plus 3. And I recognize at this point that I have 5k minus 4k plus 3. That is my n is equal to k situation. So I'm going to rearrange this into 4, 5 to the power of k minus 4 plus 5 to the power of k minus 4k plus 3. This stuff here is divisible by 4 by assumption, minus 4 is divisible by 4, straightforwardly, and any number multiplied by 4 must also be divisible by 4. Or any whole number or multiplied by 4 must be divisible by 4. So I have now shown that all of these things are divisible by 4 individually, so they must be divisible by 4 altogether. And now I can write down my final statement, which is going to be pretty identical to what it always is. So I'm just going to write it down and come back to you. So same statement as we usually write down. As n equals k plus 1 is true if n equals k is true, and we have shown that n is equal to 1 is true, therefore the n equals k plus 1th position must also be true, which would be if we start at n is equal to 1, the second position would be n is equal to 2. If n is equal to 2 is true, that proves that n is equal to 3 is also true, and by leapfrogging our way up the number line, we show that it must be true for all values of n greater than or equal to 1. So this is how our divisibility proofs are generally going to work. You need to start with n is equal to k plus 1. Again, to this line here should give you 50% of the marks. Then we are breaking up our k plus 1th power into some clever breakup that gives us something divisible by what we're looking for, in this case 4, and then usually multiplying by 1, but we've seen that it isn't always multiplied by 1. So as a general rule of thumb, you're going to break up the number in front of your power piece into the number you want to divide by plus whatever is left over. That is not guaranteed to always be the case, but it is a very good rule of thumb for divisibility proofs. So I want to be able to divide by 4, so I broke 5 up into 4 plus 1. So you're going to break up your number in front of the power into what you want to divide by plus whatever is left over. And that will usually get you out. And that is all there really is to our divisibility proofs. You can see that they follow a very similar pattern each time, where we're starting with n is equal to k plus 1 and kind of doing a substitution type idea at the end to say that because we've assumed n is equal to k is true, that means that this block must be divisible by 4, and then we should have everything else multiplied by 4 or a multiple of 4, and therefore they're divisible by 4 as well. And then we don't forget that we have to write out part 4 of our proof. So you can see the structure is very rigid, and the marking scheme requires you to write everything out in this type of form. And that's what we need for divisibility.